Welcome to week 5, everybody. While I'm doing the intro, please take out some paper for notes, and also if you have graph paper in your binder, it would be helpful to have that as well if you would like to write down the examples that I am going to walk you through while you're doing that. So we've been talking about quadratics and factoring. We've talked about several different kinds of factoring at this point. We're going to take a little sidestep from factoring to talk about features of quadratics. And then we're going to go back to a couple more types of factoring that we haven't covered yet. But hopefully soon you'll be able to see why we're going to take a little sidestep here. Okay, so factoring. When we were talking about factoring, we talked about several different types. And we were talking about those types in terms of what kinds of factoring you could use in order to find their solutions. So when I saw an example that looked something like f of x equals x squared minus 4x minus 5. If you guys saw just this part of it, you would be able to use simple factoring and get that to be what you need it to be. But when we're talking about quadratic features, we're talking about the different things about this particular quadratic that we can point out. So one of the things that we can do that is very helpful for when we're first starting is using your graphing calculator. So hopefully you guys have those still. If you don't have it, remember you can go to Desmos online and you can use their graphing calculator. So when we look at something like this first example, if I was to put this into my y equals x squared minus 4x minus 5. Now, I know that this is a quadratic. 1, because it makes a U-shaped graph. And 2, because it has this x squared in it. When it has x squared, I know that it's a U-shaped graph. Okay. When you're graphing quadratics, you can use your graphing calculator to find the points to help you graph them. We know that this is true. You can go to second table and you can use some of the points that are on here to graph on some graph paper what this would look like. I want to point out that when you're looking to graph a quadratic, one of the things that's really helpful to do is find the place where you see symmetry in the graph. And what I mean by that is, I'm going to scroll down a little bit. See here, it goes from 0 to -5 to -8, -9, -8, -5, 0. This is symmetry with this 2, -9 in the middle here being kind of like that point where it stopped, where it's symmetrical on either side of that. So when I think about using a table to graph, I want to find this like bridge of symmetry when I'm looking at quadratics. I'm going to then use these points to graph. So just to make this a little easier, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. Okay, so -1, 0, 0, -5, 1, -8, 2, -9, 3, -8, 4, -5, and 5, 0. So I have these points which I use my graphing calculator to find. This parabola, or quadratic, would be the graph of f of x. Now, you could have also taken and put -1 in here and here for x and found out what that was supposed to be, and then 0, and then 1, or however you wanted to do it. But this way is just a little bit easier. Now that we have this, there are several things that we're going to talk about that are features of quadratics. And I'm going to kind of go back and forth between having this page that has the example on it and this page which I have for notes. So the first thing that I want to talk about is this word called the vertex. The vertex is the point you know, like XY, the point, that is the maximum or minimum of the parabola. So I'll move that over a little bit. There we go. So what I mean by maximum or minimum is that if you have a parabola that opens up like this, because it's something like the form of x squared, this point here at the bottom is going to be its vertex. But this vertex is going to represent a minimum value because it's the lowest that it goes on this parabola. Versus if I have a parabola that opens down, this point that's the vertex is going to be a maximum because it's the furthest point at the top or the apex of this parabola. Okay, so when I look at this, when I'm looking here for the vertex, I'm noticing this here is my lowest point on this graph. So the vertex, and remember we said that it's a point, so it gets written as a point, happens at 2, -9. Like that. Okay, the second feature is called the axis of symmetry, or axis of symmetry. The axis of symmetry is the line that divides the parabola into two congruent halves. This line always passes through the vertex. Okay. Now, often it's really easy to just look at a parabola and tell where that axis of symmetry is, but sometimes it's not. So instead, in those cases, what we can do is you can use the formula to find what it is, and the formula is simply this. It's x equals -b over 2a. So, for example, if I'm looking at this one, the line that would cut this in half so that the two sides were symmetrical would be this line right here. And I know that vertical lines happen when x equals a number, and that x here would be a +2 because I'm over here at +2. So the axis of symmetry would be the line x equals 2. And if I had wanted to use the formula instead, remember we said that x equals -b over 2a, then this would be equal to negative of -4 over 2 times a, 2 times 1, which would be 4 over 2, or 2. So x equals 2. As a reminder, remember with these that it's really ax squared plus bx plus c. That's where I get the a, the number out front, sorry, and then the b, the number here out in front of this x, and then c is the constant on the end. Okay, so that is my axis of symmetry, this line that makes it directly in half. Okay, the next thing that we're going to talk about are intercepts. There's two types. The first type are x-intercepts. X-intercepts are where the graph crosses the x-axis. It can also be found, it can be found by observation of a graph, or by setting y equal to 0. So if I'm looking for the x-intercepts, I'm going to set the y equal to 0. So if I go back to my example here, if I was looking here for the x-intercepts, on the x-axis, the place where the graph passes through are here at -1 and here at 5. So those two would be the x-intercepts. So for intercepts, I'd have x-intercepts at -1 and 5. But it's not always that easy to tell where they are. Sometimes you'll have to do it by taking and putting y in for 0. We talked previously about how f of x is really like y. So if I was to try to do this, I'd have y equals x squared minus 4x minus 5. And I said that to find my x-intercepts, I set y equal to 0. So if y is 0, the only thing that's changed so far is that. But we talked about this before, how this is kind of like our simple factoring. If we needed to, we could break this up. Things that multiply to 5, 1 and 5, gets to a -4, so that means the negative has to be here, and this would be a positive, and I would split these into the two cases. X plus 1 equals 0, and x minus 5 equals 0, so x has to be -1, and x has to be 5. So this was showing this by observation, and this one is showing it by solving. In either case, you get the same two values. Okay. The other type of intercepts, we have this x-intercept. The next type is y-intercepts, which is the same thing, it's just backwards. So y-intercepts are where the graph crosses the y-axis, can be found by observation. So same thing as above. Or, and in this case, because it's a y-intercept, I'm going to say by setting x equal to 0. So for y-intercepts, I set x equal to 0. For x-intercepts, I set y equal to 0. It's always the opposite. Okay, so when I take a look at my y-intercepts, I'm looking for the place that it crosses the y-axis. Well, I can see right here, I graphed it a little clumsily, but it should have crossed right here at -1, 2, 3, 4, 5. So my y-intercept should be at -5. It's the only time that it crosses there, so there's just one of them. But if I needed to solve for that algebraically, I would take this same thing, and this time I would insert 0 for x instead of y. So to find my y-intercept, I set x equal to 0, so I'd have 0 squared minus 4 times 0 minus 5, 0, 0, minus 5. So y would be -5. All right. The last thing is called end behavior, which we've actually talked about before. End behavior is simply taking a look at the domain and range. Okay. And we've talked about that before. So if I look at this and I'm trying to figure out the end behavior, Well, for my domain, my x values are going to continue on and on in this direction, on and on this direction. So my domain is going to go from negative infinity to positive infinity. Remember, the lower number always goes on the left, the higher number goes on the right. I can't include an infinity symbol because it goes on and on forever. The other way that you could write this is by doing it like this. That's fine as well. They mean the same thing. The range. Now, in this case, I want the lowest number. So I'm going the lowest down here. Well, the lowest is this -9. So that's going to go on this side. This is included in the range. So I'm going to do a close bracket. And this goes on and on and on forever in the positive direction. So to positive infinity, open bracket. And again, if you wanted to, you could write it the other way. Just this time it would be included, so I would use this symbol instead. And infinity. Oh, you know what I noticed? I wrote y up here instead of infinity. There we go, fix that. Oh, and it's because I meant to write y down here. Because we're talking about range, we're talking about the y values. All right, glad I noticed those two things. All right, so let's look at some more examples then. Because this was an example where we had some kind of like simple factoring in order to find this, but can you use this same type of end behavior and features of quadratics with other types? So let's take a look at a second example. Say for our second example, we have something like g of x equals x squared minus 4x. Now again, if I was to look at that like this, we notice that this time, both of these terms have something in common. So this is like a GCF question. We're going to take out the thing that they have in common. But let's move on first. Let's first take a look at graphing these. So I'm just going to start by going in and I'm going to erase this. I'm going to put in the x squared minus 4x, and I'm going to go to my table and I'm going to look for symmetry, and hooray, it's already there. So if I'm looking here, I got 5, 0, -3, -4, -3, 0, 5. So I'm already at that point of symmetry. I'm just going to take these points and graph them. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so -1, 5, 0, 0, 1. Oh, you know what I just noticed? I had to put that at 4, didn't I? 1, 2, 3, 4. Yes, I did. 1, -3. 2, -4. And then I'm going to come up, and this is going to be symmetrical on this end like this. And now here is my parabola. All right, so let's talk about features. Where's the vertex? Well, the vertex is that point at the max or min. So right here at 2, -4, that would be my vertex. Where's or what is the axis of symmetry? Remember, that's written as a line. As you do these, you're going to start to notice something. Here's my axis of symmetry. I would have x equals, because that's when I have a line that's vertical like this, it's always x equals. It's a +2. Notice that this x equals is always this number right here, because the axis of symmetry always goes through the vertex. What are the intercepts? So we've got our x-intercepts. I've got one here at 0 and one here at 4. So 0 and 4. The y-intercepts, well, there's one here at 0. Now remember, if you needed to find those algebraically, if I wanted to find my x-intercepts, I would set y equal to 0. So in this case, g of x is like my y, so 0 equals x squared minus 4x. Like I said before, I could take an x out of both of those, and I would split into the two cases. X is 0, or x minus 4 is 0. So x is 0, that's already solved. I would add 4 to the other side. I get 0 and 4, 0 and 4. If I wanted to find my y-intercepts algebraically, I would set x equal to 0. So I'd have y equals, put the 0 in for x, 0 squared, minus 4 times 0, 0 minus 0. So y would be 0, which is what we got here. Last thing to talk about is the end behavior. So domain, again, going on and on in both directions. So we've got negative infinity to positive infinity. And the range goes from -4 to infinity. So my range, I'm going to include the -4 and go to infinity. Let's try another one. So the next one could actually be solved two different ways. It could be solved by perfect squares, or it could be solved by taking the square root. We're going to call this is third one, h of x. So h of x equals negative x squared plus 9. All right, so if I go in, back into here, get rid of this, negative x squared plus 9. I'm looking for symmetry, and I'm finding it right here. So from -3 to +3. So -3, 1, 2, 3, 0. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Next one, -2, 5. -1, 8. 0, 9. And then coming back on the other side. Now this time I've got a parabola that opens down. Not much changes though. I'm going to still start with my vertex. My vertex this time is a maximum. It's the top value instead of the bottom value, but it's still this point right here. So this point happens at 0, 9. And if I take a look at the axis of symmetry, x equals what number? Well, x equals 0. It's also the y-axis. Intercepts. My x-intercepts. Well, you can see here it crosses at -3 and +3. And my y-intercept happens at +9. If I had wanted to find those algebraically, I know I keep harping on that even though it's really clear. That's because we're going to get to an example where it's not going to be super clear. If I wanted to do this algebraically, to find my x-intercepts, I have to set y equal to 0. So in this case, h of x is like y. So 0 equals -x squared plus 9. Now for this one, you could add the x squared to both sides. Oops, should be an equal sign. And then take the square root of both sides, and you would get x equals positive or -3, which is what we got, positive or -3. You could have also, going back to this step, maybe recognize that this -1 out front really shouldn't be there, because we hopefully have talked about that before when you're factoring these. So if I pull that -1 out, actually I'm not sure we've done an example like this, but I'm glad it's coming up. We can break this down into x and x, and 3 and 3. This is the perfect squares example where you have plus or minus. If I divide both sides by -1, that goes away. So I just have x plus 3 equals 0 and x minus 3 equals 0. So again, I get x equals 3 and x equals -3. Either way that you do that, either using the square root or the perfect squares. Either one's going to work. And then for the y-intercept, remember I set x equal to 0. So I would have y equals -0 squared plus 9, or 0 plus 9, which is 9. Last thing here is end behavior. In this case, my domain, even though it's pointing down, it's still going on and on forever in both directions. So negative infinity to positive infinity. And my range this time, well, my range, remember I always start with the lower value, and it's coming up from this negative infinity, and ends here at this positive 9. So I'm going to close it there at 9. All right, last one. And the last one's the trickiest one, in my opinion. Number 4. Number 4 is kind of like an example we would use if we were going to do something like the ninja trick or something like that. So in this one, I'm going to call this one j of x. Let's call this 2x squared plus 3x minus 9. And again, if you guys saw that, you could do the ninja trick and come up with the 2 factors, slash solutions, slash roots, all of those things that you come up with for your x-intercept. Whatever values that you find for your x-intercepts, those are your roots, your solutions, your zeros. All of those mean the same thing. I'm going to write that down because I want you guys to have that for your notes, but let's focus on this one for just a second. All right, I want you to go into your calculator and oops, that's me, sorry. And let's put this new one in. 2x squared plus 3x minus 9. I'm going to go to my table. If I push the right buttons, you can see that it's a parabola, and that's what it looks like. And I'm going to look for where it's going to have this symmetry thing. Well, when I'm looking here, I see a 0 and a 5 with some negatives in between. So like that looks like it should be the place where the symmetry is happening, but those numbers don't appear right. And you could change your table and to maybe like a half. And maybe then it'll start to, oh, yep, sure does. Now it's starting to look like symmetry again, but it's still not quite right because I don't have a middle point. So with these ones, it's a little bit trickier. There is a way to get around it though. You probably noticed on the other ones, do you remember with our intercepts that was the place where we were at here? So like there's each time that happens, these 2 points are x-intercepts. So there's a couple of different ways that we can do this. One would be to find the intercepts and to find the vertex, and then you can kind of sketch the graph. So we can go that route. I would say at first, when you're looking at this graph and even the table of this, I'm not quite sure where the vertex is because it looks like it's going to be between -1 and -1.5. But then what would the value on the right be? So like, let me hold off for a second on naming the vertex. I'm just going to kind of leave this over here for a second. And when I look at the graph of this, it looks like the axis of symmetry is somewhere like -1, but I can't be positive about that. So remember that for the axis of symmetry, one of the things that we said you can do is if you needed to confirm or just do it with like algebraically, is to use that x equals -b over 2a. So let's do that. I've got negative 3 over 2 times 2. So my axis of symmetry is happening at negative 3/4. X equals negative 3/4. So somewhere really close to 1, but not really 1. So if I was to put that in, I'm just going to sketch that in really lightly, like that. That would be my axis of symmetry. Now, the other thing that we can do with that is, we said that this axis of symmetry, this x is always the x value in my vertex. So I could take this x value and put it in to my equation and figure out what y is supposed to be. So if I know that x is 3/4, then I can do 2 times negative 3/4 x, negative 3/4 squared plus 3 times negative 3/4 minus 9. And if you were to put that all into your calculator, you'd get negative 10.125. See, that is kind of a weird number, right? No wonder it came out funny on here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So negative 10 and a teeny bit more. So our vertex is going to be somewhere around there. Negative 3/4 and negative 10.125. Next thing, can you find intercepts? Well, sure we can. We said that if we wanted to find the x-intercepts, what we could do is set y equal to 0. So this case, j of x is like y, so 0 equals 2x squared plus 3x minus 9. So in this case, I'm going to use my ninja trick just to make my life a little bit easier. So plus 3x minus 18. Things that multiply to 18 but add to 3, 6 and 3. I need it to be a positive 3, so plus 6 and minus 3. I get to this point, I made it disappear by multiplying, and make it reappear by dividing. So 0 equals x plus 3, and 2x minus 3, because these do not divide evenly. So either x is negative 3, or x is 3/2, like that, or 1.5. So one of my x-intercepts is going to be at negative 3, and the other one is going to be at 3/2, or 1.5. So negative 3, 1, 2, 3, and 1.5. So I can sketch now this parabola. Oh, that was not a good sketch. Hopefully yours is a little more rounded than I just made mine. There we go. Like that. If I wanted to find my y-intercepts, I would have to set x equal to 0. So 2 times 0 squared plus 3 times 0 minus 9. So y is negative 9. So it crosses here at negative 9. Last one, end behavior. So with our end behavior for our domain, once again, there's no limit on the domain, so negative infinity to positive infinity. And my range, the lowest value right here, is negative 10.125, and it goes to positive infinity. All right, hopefully you guys will reach out to me if you have any questions as you're working on features of quadratics exercises for this week. Hope that you had an enjoyable Easter with your family and that everyone is safe and well. Bye.